Now, exercise of chapter 4, example 4.1. A circular coil of wire consisting of 100 turns, each of radius 8 centimeter, carries a current of 0.4 ampere. What is the magnitude of the magnetic field at the center of the coil? Now, see here, the number of turns given to you, that is 100. Radius, that is 8 centimeter, so that is 0.08 meter. Current flowing through it, that is 0.4 ampere. What is the magnetic field B that we want to calculate at the center of the coil? So we have the equation for the magnetic field at the center of the current carrying coil, and that is B equal to N mu 0 I upon 2R. N is given to you 100. Mu 0, that is 4 pi into 10 raised to minus 7. Current I, that is 0.4 ampere. 2, and radius R, that is 0.08 meter. Now solve this one, you will get answer. Clear to all of you? Now example 4.2. A long straight wire carries a current of 35 ampere. What is the magnitude of the field B at a point 20 centimeter from the wire? Now see, current I through the wire, that is 35 ampere given to you, and we want to find the magnetic field at a point which is at 20 centimeter, means at point 2 meter from the wire. So R, that is 0.2 meter, and B that we want to calculate. Now magnetic field at any point due to current carrying wire. For that we have equation B equal to mu 0 I upon 2 pi R. Mu 0, that is 4 pi into 10 raised to minus 7. I, that is 35. 2 pi. R, that is 0.2. Now solve this one. You will get the magnetic field at the given point. Clear to all of you? 4.3. A long straight wire in the horizontal plane carries a current of 50 ampere in north to south direction. Give the magnitude and direction of B at a point 2.5 meter east of the wire. Now see, current, that is 50 ampere, is in the direction north to south. Now the point is at distance 2.5 meter from the wire. We want to calculate magnitude of magnetic field at that point, as well as we have to fix its direction. Now the equation for the magnetic field at any point due to current carrying wire, that is mu 0 I upon 2 pi R. Mu 0, that is 4 pi into 10 raised to minus 7. I, that is 50. 2 pi. R, that is 2.5. Now solve this one. You will get the answer of magnetic field. Now the direction of B, that will be vertically upward. So this you can fix with the help of right hand rule. Say, suppose we consider the directions like this, in this way. So this one is north, this is south. So current is from north to south. So if we place the right hand thumb in the direction of current, so in this direction, then fingers are going downward from this side. So from this side it will move up. So this is east, this is west, north, south. It implies that if your point that is on east side, then the field line that is coming out from east side means the direction is tangentially at any point. So it is vertically upward. Clear to all of you? Now example 4.4. A horizontal overhead power line carries a current of 90 ampere in east to west direction. What is the magnitude and direction of the magnetic field due to the current 1.5 meter below the line? So current that is 90 ampere, the point is at 1.5 meter, and we want to find the field at that point. So B, that is mu 0 I upon 2 pi r. Mu 0, that is 4 pi into 10 raised to minus 7. I, that is 90. 2 pi r, that is 1.5. Solve this one, you will get the answer. Again here, you can fix the direction by right hand rule. See, in this way, if we consider the directions north, south, east, west. Okay. Now east to west current is there. So if you hold the right hand thumb like this, then from lower side, the field lines are coming out. So if we draw the tangent, then tangent that will be towards me. So north to south means towards me, that is the southward direction. So direction of the field, that is southward. Clear to all of you? 4.5. What is the magnitude of magnetic force per unit length on a wire carrying current 8 ampere and making an angle of 30° with the direction of the uniform magnetic field of 0.15 Tesla? Now, current through the wire, that is 8 ampere, it is placed at angle 30° with respect to the direction of the magnetic field, and magnetic field, that is 0.15 Tesla. Now, in theory, we derive the equation, the force acting on the current carrying wire in the uniform magnetic field, that is IL cross B. So magnitude wise, we can write that is ILB sine theta. So magnetic force per unit length. So take this length on left hand side. So force upon length will give you the force per unit length. So that is IB sine theta. I, that is given to you 8 ampere, theta that is 30, so sine 30, and B, that is 0.15. Now solve this one, you will get the answer. Clear to all of you? 4.6. A 3 centimeter wire carrying a current of 10 ampere is placed inside a solenoid perpendicular to its axis. The magnetic field inside the solenoid is given to be 0.27 Tesla. What is the magnetic force on the wire? So, length of the wire, that is given to you 3 centimeter. So that is 3 into 10 raised to minus 2 meter. Current through it, that is 10 ampere. Magnetic field inside the solenoid, that is 0.27 Tesla. And we know this thing, inside the solenoid, the magnetic field, that is along the axis. And here the wire is placed perpendicular to the axis. It implies that wire is perpendicular to the magnetic field. So theta is 90. Now what is the force acting on it? So we know when any current element IDL is placed in the magnetic field B, the force acts on it, that is IDLB sine theta. I, that is 10 ampere, DL, that is 3 into 10 raised to minus 2, B, that is 0.27, theta, that is 90, so sine 90. Now solve this one, you will get the answer. Clear? 4.7. Two long and parallel straight wires A and B carrying currents of 8 ampere and 5 ampere in the same direction are separated by the distance of 4 centimeter. Estimate the force on a 10 centimeter section of wire A. So current I1, that is 8 ampere, current I2, that is 5 ampere. Separation between these two parallel straight wires, that is 4 centimeter. So that is 4 into 10 raised to minus 2 meter. We have to estimate the force on 10 centimeter section. So we have to consider L, that is 10 centimeter. So that is 0.1 meter. Now F is how much? So we have the equation for the force between two parallel currents separated by distance d per length L of it, that is mu 0 I1 I2 L upon 2 pi d. So F, that is mu 0 is 4 pi into 10 raised to minus 7, I1 8, I2 5, L, that is 10 into 10 raised to minus 2 upon 2 pi. Separation means distance between two wires, that is 4 centimeters. So that is 4 into 10 raised to minus 2. Now if we solve this one, we will get the force. Clear? 4.8. A closely wound solenoid 80 centimeter long has 5 layers of windings of 400 tons each. The diameter of the solenoid is 1.8 centimeter. If the current carried is 8 ampere, estimate the magnitude of B inside the solenoid near its center. Now length L, that is 80 centimeters, so 0.8 meter. Total number of tons. See, there are 5 layers and in each layer 400 tons are there. So total number of tons, that is 2000. Current, that is 8 ampere. We want to calculate magnetic field inside the solenoid. So we have the equation for the magnetic field inside the solenoid, that is B equal to mu 0 N I, where N, that is the number of turns per unit length. So here total number of turns and total length, that is given to you. So number of turns per unit length will be capital N, the total number of turns, divided by total length. So substitute here small n, that is capital N by L. So B, that is mu 0 capital N I upon L. Mu 0, that is 4 pi into 10 raised to minus 7. N, that is 2000. I, that is 8. L, that is 0.8. Now solve this one. You will get the answer. Clear? 4.9. A square coil of side 10 centimeter consists of 20 turns and carries a current of 12 ampere. The coil is suspended vertically and the normal to the plane of the coil makes an angle of 30 degree with the direction of uniform horizontal magnetic field of magnitude 0.8 Tesla. What is the magnitude of torque experienced by the coil? Now, simple thing again, area, that is 100 centimeter square. So that is 100 into 10 raised to minus 4 meter square, that is 10 raised to minus 2 meter square. Number of turns in the coil, that is 20. Current flowing through it, that is 12 ampere. It is placed in the magnetic field B of 0.8 Tesla, and the angle between area vector and the magnetic field, that is 30 degree. So tau is how much? Now we have the equation of torque tau acting on the current carrying rectangular coil placed in the uniform magnetic field at angle theta, that is NIAB sine theta. N, that is 20, I, that is 12, area, that is 10 raised to minus 2, magnetic field B, that is 0.8, sine 30. Now solve this one, you will get the torque acting on the coil. Clear? 4.10. Two moving coil meters M1 and M2 have the following particulars. R1, that is 10 ohm, N1, that is 30, A1 3.6 into 10 raised to minus 3 meter square, and B1, that is 0.25 Tesla. For second meter, R2, its resistance that is 14 ohm, total number of turns N2, 42, its area A2, 1.8 into 10 raised to minus 3 meter square, and is in the magnetic field B 2.5 Tesla. The spring constants are identical for the 2 meters. Then determine the ratio of the current sensitivity and voltage sensitivity of M2 and M1. Now see, the spring constants K1 that is equal to K2 that is K are given to you, identical one. Then for both the meters, resistance, total number of turns, area, and the magnetic field in which the coil is placed, that is given to you. Now we have the equation for current sensitivity, that is IS equal to NAB upon K. So current sensitivity of second meter upon current sensitivity of first one, that we can write equal to N2A2B2 upon K divided by N1 A1 B1 upon K. Now K cancelled. N2 42, A2 1.8 into 10 raised to minus 3, B2 0.5 upon N1 30 into A1 3.6 into 10 raised to minus 3 into B1 0.25, that is equal to 7 by 5. Now voltage sensitivity. So equation of voltage sensitivity, that is NAB upon RK. R, that is the resistance. So voltage sensitivity of second one upon voltage sensitivity of first one equal to N2A2B2 upon R2K divided by N1A1B1 upon R1K. K cancelled again. So N2A2B2 into R1 upon N1A1B1 upon R2. But see here, we already calculated this ratio of the current sensitivity, and that is N2A2B2 upon N1A1B1, and that is 7 by 5. So in this equation, substitute this part N2A2B2 upon N1A1B1 directly 7 by 5. Now resistance R1 that is 10, resistance R2 that is 14. So you will get the answer 1. Clear to all of you? 4.11. In a chamber, a uniform magnetic field of 6.5 Gauss, 1 Gauss that is 10 raised to minus 4 Tesla is maintained, and electron is shot into the field with a speed of 4.8 into 10 raised to 6 meter per second normal to the field. Explain why the path of the electron is a circle. Determine the radius of the circular orbit. Charge of electron that is 1.6 into 10 raised to minus 19 coulomb. Here printing mistake છે, સુધારજો. Mass of electron that is 9.1 into 10 raised to minus 31 kilogram. Now see here, the magnetic field that is 6.5 Gauss, that is 6.5 into 10 raised to minus 4 Tesla. Speed that is 4.8 into 10 raised to 6 meter per second. Charge E that is 1.6 into 10 raised to minus 19 coulomb. And mass of electron that is 9.1 into 10 raised to minus 31 kilogram. Now, what is the radius of the circular orbit that we want to calculate? So here, the electron will execute circular motion. Why? Because the force acts on the charge Q in uniform magnetic field B, that is Q into V cross B, V that is the speed of the charge. So force that will be perpendicular to velocity and magnetic field both. When the force is perpendicular to the velocity, the particle will execute circular motion. And now the required Centripetal force for the circular motion mv square by r will be provided by magnetic force, that is QVB. Here Q, that is E. So we can write EVB. Sine theta, that is sine 90, is 1 because V and B are perpendicular, that is given. So radius of its circular path, that is mv upon EB. M, mass of electron 9.1 into 10 raised to minus 31. V, that is 4.8 into 10 raised to 6. Upon charge E, that is 1.6 into 10 raised to minus 19. Into B, that is 6.5 into 10 raised to minus 4. Now solve this one. You will get the radius of its circular path. Clear to all of you? 4.12. In exercise 4.11, obtain the frequency of revolution of the electron in its circular orbit. Does the answer depend on the speed of the electron? Explain. Now see, the frequency, that is EB upon M, that is the angular frequency. So angular frequency is 2 pi f, that is EB upon M. So frequency f, that is EB upon 2 pi m. Directly you can write this equation of the frequency also. Now frequency f, that is E 1.6 into 10 raised to minus 19. B, that is 6.5 into 10 raised to minus 4. 2 pi m, that is 9.1 into 10 raised to minus 31. Solve this one, you will get the frequency for the revolution of electron. And here, does the answer depend on the speed of the electron? No, it does not depend. Why? Because see the equation of the frequency, that is EB upon 2 pi m. So here we can see this thing. The speed is not appearing anywhere in the equation. So answer does not depend on the speed of the electron. Clear to all of you? Now 4.13. A circular coil of 30 turns and radius 8 centimeter carrying a current of 6 ampere is suspended vertically in a uniform horizontal magnetic field of magnitude 1 Tesla. The field lines makes an angle of 60 degree with the normal to the coil. Normal to the coil means with respect to area vector. Calculate the magnitude of the counter torque that must be applied to prevent the coil from turning. B. Would your answer change if the circular coil in A were replaced by the planar coil of some irregular shape that enclose the same area? All other particulars are also unaltered. So here the counter torque required to prevent the coil from turning, that should be exactly equal to the torque acts on the coil under the effect of which it will be rotated. So here the given data, number of turns 30, radius of the coil, that is 8 centimeter, so 8 into 10 raised to minus 2 meter, current through it, that is 6 ampere, B, magnetic field, that is 1 Tesla, theta, that is 60, and area that we can write pi r square. So torque applied, that is equal to torque x on it. So torque tau, that is n I a b sine theta. N, that is 30, I, that is 6, A, that is 3.14, B, that is 8 into 10 raised to minus, pi r square. So area, that is pi r square, pi 3.14, r, that is 8 into 10 raised to minus 2 square of 8. Then B, that is 1 sine theta, that is sine 60. And now solve this one, you will get the answer. Clear? Now question B. Here answer will not be changed if the circular coil is replaced by the planar coil, because Here the torque that does not depends on the shape of the coil. It depends only on the area enclosed by the coil. So here area enclosed by the coil with irregular shape, that is same one. So your answer that will not be altered. Clear to all of you?